Hi, my name is Chenpu Wang. I will present static Taylor expansion, which is a new and path-independent method for uncertainty analysis. The code to generate the data is on the GitHub, as shown here. First, this is a line talk, so I will present a table of content. First, I will talk about foundation for static Taylor expansion. Then I will talk about validation standards. Then I will talk many of the applications. Finally, I will give a summary and discussion. Let's start with the foundation of static Taylor expansion. I will compare it with existing arithmetics, present its foundation formulas, discuss convergence, and present how to calculate reliability of the result. Finally, I will focus on its fundamental property to be able to trace dependency, which lead to path independence. Why static Taylor expansion? We know Taylor expansion enables to calculate analytic function, namely, if you have a function with an input variable x. Using Taylor expansion, you can calculate the value near x. Static Taylor expansion just replace the variable x with a random variable with mean and standard deviation to calculate result, mean, and standard deviation. It accounts for the actual distribution. Here, rho is the distribution density function and the sample count to calculate reliability of the result. And also, the input, the quality of the measurement of the mean plus standard deviation is measured by precision, which is the standard deviation divided by the absolute value of the result. And this measurement quality goes into static Taylor expansion directly. A smaller px means a higher quality of the measurement. In conventional floating point arithmetics, it only calculates the result value without delta f. And worse, the result in f contains rounding errors. In interval arithmetics, its input is a range rather than mean or standard deviation. So it has a different context than statistical context. Significant arithmetic is a numerical approach, while static Taylor expansion is analytic approach and is a mathematical rigor. So arithmetics add as a random value to x and do it many times and use statistics to calculate the result mean and standard deviation. So it is a sampling process and is extremely heavy in calculation, while static Taylor expansion is a direct characterization. The floating point arithmetic and the interval arithmetic has one problem. Actually, all of this arithmetic has one problem. It means path dependence. The result depends on how you carry on this calculation. For example, in floating point arithmetics, when we try to invert a matrix, we have to use Gaussian elimination to minimize rounding errors rather than use a direct matrix inversion. And in this path dependence problem is much worse in interval arithmetics. In contrast, static Taylor expansion is path independence. because it can trace dependency within this function. Before we go to the static Taylor expansion, we need to discuss two concepts, distribution pole and distribution zero. Suppose I have function yx, and I need to find the distribution density function of y from if I already know distribution density function of x. Here is the standard formula. The distribution pole happens when the first derivative of y to x equal to 0. That means the density function go to infinity. Well, distribution 0 happens when the first derivative of y to x is infinity, and the diffusion density function of y goes to 0. Here are two examples. Here, we are counting y equal to x squared, and the y-axis is a probability density. The x-axis is a square root of y, and the deviation is always 1, but the mean is changed from 0, 1, 2, 3, 4, and 5. And you can see at 0, the distribution density function is infinity. And here is another example. We're calculating y equal to square root x. And this time, the y-axis is scaled as y squared. And you can see at x equal to 0, all density functions are 0. There's some similarity between these two pictures to display distribution pole and distribution 0. That means when the mean is 5, they all look like a Gaussian distribution. In other words, when the distribution pole or distribution 0 are pretty far away from the mode of the distribution is not disturbed. And because of that, we could think about it. When the pole or 0 are far away from the distribution mode, we can use the same way to characterize the uncertainty or the output uncertainty. Now, let's go present the foundation formula for static Taylor expansion. Before that, I will introduce some definitions. If we can use this formula to normalize distribution density function so that it has a mean of 0 and deviation of 1. For example, normal distribution is the normalized distribution of Gaussian distribution. Once we have a normal distribution, we can define a bound momentum, which is the integration between two range and with z to the n order using this formula. And there is one constraint for this bounded moment. It's called mean reverting condition. That means when the n is 1, this has to be 0. That means the lower bound of the integration is determined by the upper bound. And a special case is if the distribution is symmetric, as shown here, then the lower bound and upper bound are symmetric, and that also means all the even order of bound momentum is 0, as shown here. A special case is a uniform distribution is equal is a it is normalized distribution is a constant, but its range is square root 3. So here is a Taylor expansion, standard Taylor expansion formula, right? And we have x, and we have a small value 2x, right? 2x. And we can use Taylor expansion. But if we use normalized distribution, the formula changes slightly, right? Then we integrate this over the distribution range, and there's a difference between the mean of the function, output function, to the value of the function, and we define this as uncertainty bias. And it is determined by the standard deviation, by the deviation of the input and the bounded momentum and the Taylor expansion. At the same time, we can determine the output variance using this function, right? It's still in the similar formula, but a little bit more complex. Standard Taylor expansion, two-dimensional. The standard Taylor expansion has a condition called uncorrelated uncertain condition, which means without systematic error, any two input variable to the static Taylor expansion can be considered to be independent each other, so that their combined probability density function equal to the product of the individual probability density function. Using this formula, we can calculate uncertainty bias as well as the variance of the result using these formulas. We'll focus on the result variance. For example, for addition using this simple formula, and for product using this simple formula. Now, let's look at the bounding momentum asymptotic when n equal to infinity. We can prove using a symmetric distribution the bounding momentum with order n and range k equal to this. Right? Here is an example for Gaussian bounding momentum, which increase with the power of range, and also for the uniform distribution, which also increase with the power of range. And the only thing is the uniform has much lower increase than the Gaussian. Using this formula, we can also estimate that this formula roughly equal to the power n of range divided by n. And this result is important when we calculate the convergence of the static Taylor expansion. Now let's give some one-dimensional examples. For example, for the exponential variance, we have this formula, and here it converges all the time because the denominator increases much faster than the top. Now, for the logarithmic, we have this formula, right? When n equal to infinity, we approach this formula, right? And we know for this sum is log n. So this is the limited value. So the convergence is determined by 1 over k. So that is a very interesting result, because to let the result variance to be limited, we have to reject the distribution rule 0 from the bounding range for the log, right? And the third one is a sine x. We have this formula. On one hand, this factor is equal to whatever we have in the exponential, so it always converges. But on the other hand, you can see this relation shows that when you expand this variance, right, this value can be both positive and negative. So the overall expansion could be negative, right? So to basically prevent that, we need to put the upper bound for the input deviation to make sure the result is always positive, no matter how many terms you wanted to expand out. Finally, for the power relation, we have this formula, and we will show that the convergence is similar to the log, which is related to 1 over k. But the thing also depends on C. When we look at this formula, we find something interesting. For the exponential, the input is deviation, but output is precision. For log, the input is precision and output is deviation. For sine x, both input and output are deviation. And for power, both input and output are precision. To make sure the convergence works, in practice, we actually, for any Taylor expansion, we basically detect if the last 20 terms of expansion are absolutely and monotonically decreasing. If this is not the case, then we say the static Taylor expansion for that particular function is not convergence. Let's look at some result of this numerical approach. For uniform distribution, we have to put upper bound for delta x, as shown in the solid line here, to make sure that the result variance is always positive. And here the x, you can see, is between minus pi and plus y. The y is about upper bound delta x, right? And if we use a uniform distribution, we have a similar picture, but the value are different, right? And you can see here, the first one is all this bound, upper bound, are periodic, same as a sine function. Second, because the uniform distribution is smaller in its bounding ranges, so that you can extend to much more terms, which result in much higher upper bound than the Gaussian, right? What is that means? That means for a periodic function like sine, your input bound for the uncertainty cannot be too larger than the period pi, quote pi. Otherwise, the thing doesn't make sense, right? The result could be anything. So now let's look at the application of convergence rule on the power function. First, for uniform, we know it has a bounding range, the calculation bounding range, equal to square root 3. We can see, this bounding range is very close to the 1 over square root 3, but increase with an exponential c. Here the x is exponential. This is kind of expected because when the S1 is a negative, the Taylor expansion coefficient becomes larger than with the expansion order n. Now, let's look at the Gaussian, and here we choose the expansion range to be 5. And you can see it has the similar thing. It is around 0.2, which is 1 over 5, right? It has almost the same trend after normalization. Why we use the range 5 first? Because there's a standard in experimental physics to distinguish these two distributions. Use sigma equal to 5 rules. Second, it's a trade-off. We know that the convergence is equal to 1 over kappa, right? And so we want to have a larger alpha, so the bound momentum is closer to the real momentum. At the same time, if we also want to have a small alpha to have small kappa to have a larger convergence range for the input. So that's why we choose number 5 here. It's a trade-off. Another thing we should notice in this picture is when we in this picture is not complete because when the value equal to a nature, when the c exponent power is a nature number, we do not use Taylor expansion to calculate the result. Instead, it's the polynomial, right? And when we have a polynomial, there should be no upper bound, right? So here the picture just ignore all this delta function at each of the nature number c here. But there is an interesting, even they have two different mechanisms, but you look at the result variance, they are continuous across each of the nature number power. Now let's talk about static binding. It is a process to determine the bounding range kappa from the input uncertainty distribution rho and the sample count n. For the first order approximation of a Taylor expansion, the formula is given by this. A special case is when fx equal to x. Here, the zeta 2 kappa is 1 kappa is the infinitive, and the less than 1 kappa is not infinitive. We can define the linear leakage as 1 minus kappa 2 kappa as zeta 2 kappa. Here is an example for the linear leakage for Gaussian distribution. It decreases rapidly with the bounding range kappa. In reality, we do not know the sample So there's a distribution mean and the distribution deviation. We only know sample mean and sample deviation. As we know, when sample size approaches infinity, the sample mean approaches distribution mean and sample deviation approach distribution deviation. And if we use sample mean and sample deviation to calculate bonding leakage, here it is relation. Namely, the leakage for using sample mean and sample deviation is always smaller than using distribution mean and distribution deviation. And here is a relation. You can see when the sample count increases for Gaussian distribution, the measured linear leakage approaches the distribution linear leakage. For example, when the sample count is 1,000 on the graph, there is almost no difference. We can define the bounding range kappa underscore s as a measuring bonding leakage. And here is then we find the equivalent, and using the linear leakage, we can find the equivalent bonding leakage, which is called the measured bonding leakage. Namely, there is the measured bonding leakage kappa is a function of the measuring bonding leakage and the sample count. From this graph, we can see when n equals n approach infinity, the kappa equal to kappa s as it defined here. And if we choose different measuring bonding range and cross section the relation of the binding cross section the linear leakage at a different sampling range, like 4, 5, 6, we got this relation. We can see the linear leakage for giving kappa hat. The linear leakage, the measured linear decrease with the sample count until reach a stable distribution linear leakage for that measuring bounding range. For example, this is for 4, 5, and 6, right? And this is a corresponding measured kappa. You can see this is a 4, 5, and 6, right? Now, let's define another ideal leakage equal to 1 minus the measured, the calculate variance of f divided by when the kappa is when the sample count is 0 is infinity, called hat variance, right? As we know, this is probably the first approximation of ideal leakage should be the linear leakage. And for the Gaussian, when kappa, the measuring kappa is 5, we see this relation, right? For fx equal to x, right? That's exactly what the linear leakage goes. We can see for different sample, for different function like a sin x, exponential x, log x, they are very close to this linear leakage. In other words, the approximation using linear leakage to calculate the ideal leakage is pretty good in this case. If we replace the function with 1 over x or 1 over x squared, the approximation is not that good. But anyway, we see that with the increase of sample count, the leakage reduces, right? And we can see the similar thing for uniform distribution. However, because uniform distribution, the bound momentum is much smaller, the linear leakage is a good approximation for the ideal leakage in all cases. And one minus that ideal leakage give us reliability. In other words, when your sample count is not big enough, the result reliability is not good enough. In this case, we can see this is the chart, how to read the reliability of leakage. Let's talk about a most important property of StatisticalTaylorExpansion, namely using dependence tracing. Using Taylor expansion, we can see the following example of dependence tracing. F plus F become 2 F divided by F, the variance becomes 0. And if X and G has a completely different set of input variables, then their variance obey the law of sum. Also, if F times F should be F squared, F divided by F to have variance 0. And if F, X, and G, Y have a completely different set of input variables, they should obey the product law. Another thing here is if we put fs into its inverse function, the result should recover the original input. Here's some example of violation of dependence tracing. We cannot calculate fgx as first calculate gx, then use the result, calculate fx. And here is the example, right? Such calculate square root square, the variance is larger than square root of square, and it's larger than the true input. Another example which is always come in the literature called path independence. We can calculate x squared minus x in various form. Only the last form gives you the correct answer, because the first form assumed x squared and x are independent of each other, while the second form assumes x and x minus 1 are independent of each other. Both forms thus give you the wrong result because of the wrong assumption. So that tells us, using StatisticalTaylorExpansion, you cannot break a calculation as a combination of arithmetic operation like a plus, minus, multiply, divide, etc. And you should also minimize conditional execution, because conditional execution may hide certain dependence in your formula. Instead, you should use a final analytic expression to calculate your result. In a way, the dependent tracing removes all the flexibility when you carry out an analytical execution, and the result you do not have dependency problem anymore. Let's talk briefly about the second section of this validation standard. The StatisticalTaylorExpansion is validated using algorithm of known result with large data set like FFT. The large data set enables high quality statistical analysis. The first thing is something called value error. It's a calculation result minus the expected known result. The second one is a normalized error, which is a value error normalized by the calculated uncertainty using StatisticalTaylorExpansion. The third thing is called error deviation, which is the deviation of the normalized errors. And also error distribution, which is a distribution or histogram of the normalized errors. The goal is to achieve ideal coverage. Ideal coverage is if the input uncertainty deviation covers all uncertainties, including the numerical error in the numerical math libraries. In the ideal coverage, there are only two kinds of error distribution, either normal distribution as shown here, because the central limit theorem, or a delta function, delta distribution as shown in the center. If, however, we do not know how the input uncertainties, a proper coverage is achieved when the error deviation is between 0, 1 and 10 instead of 1 in the ideal coverage. And if we cannot achieve ideal coverage, one way is to add noise to the input until all the input uncertainty has been specified approximately. Here, we show example of add noise. We can add Gaussian noise or add white noise. In either case, we can achieve ideal coverage with added noise. Here, the noise level is 10 to the minus 3 for the efficiency order, which we will cover later. Now, let's go to the third section of our talk called application. We'll talk about matrix inversion to distinguish between distribution test and the value test. We'll talk about mass function and to study distributional pole and the rounding errors. And using polynomial, we'll study in greater detail of rounding errors and the distribution poles. We will use FFT to study the numerical error in library function and its great effect on the final result. Finally, we will use regression to show that we can use precision to detect catastrophic. Let's start with our first application to use StatisticalTaylorExpansion to find the variance of matrix determinant. Let's do some review first. Suppose we have a nature sequence from 1 to n. We can create an ordered permutation from it by pick m number from it to construct ordered permutation as shown here. We can then permutate this ordered permutation to obtain an unordered permutation together with its sign. And we can have a matrix of size n, namely, it contains n squared of variables. Each has a row index I and a column index j. And we can create a matrix of it, giving ordered permutation of row indexes and an ordered permutation of column indexes. We just delete all the rows in the row index and all the columns in the column index, and the remaining is a submatrix. From the from the ordered permutation and unordered permutation, we can define the determinant of the matrix, and we can prove that the determinant of the matrix can be expressed as a sum of unordered as a sum of submatrices times the corresponding products. And using this formula, we can come up with the variance of the matrix using this formula. We can also define something called a Jagged matrix, which is defined in this. The important property of the Jagged matrix is product with the matrix equal to the determinant times identity matrix. And from the Jagged matrix, we can define the inversion of the matrix using this formula. However, the convention wisdom is we should never use this formula of definition to calculate inverted matrix. Instead, we should use a Gaussian elimination. Gaussian elimination is just a path-dependent method, but optimized path to minimize rounding errors, which works against the principle of StatisticalTaylorExpansion, which is path independent. Let's look a little more in this matrix inversion problem. We come up with the idea of matrix stability, namely, if an element is changed a little bit, how much the result would change due to our method of calculation. And this one is characterized by something called condition number. In fact, if we look at this matrix inversion formula, we find that the determinant matrix is at the denominator, right? So this one, the precision of the denominator properly determines the precision of the end matrix inversion. And we clearly see here the x-axis is condition number, and the y-axis is determined precision, and this shows a relation between the condition number and determined precision for many random generate matrices. Each has a different condition number and the corresponding precision. We can clearly see there is a clear linear relation between condition number and the determinant of precision. And we can also add in this graph Hilbert matrices, which are theoretically most unstable matrices. We can see all these Hilbert matrices are on the same linear relation with this random matrices. So it's a proof that we can use determinants of precision to replace condition number, and determinant of precision has a very clear meaning what it is. And here we redeflate the formula for determined variance. It's very complex already, but if you imagine each element is under both the numerator and the denominator, And the inversion of the matrix is very complicated when using StatisticalTaylorExpansion. I think the answers call for analytic softwares like Mathematica. Let's test the matrix determinants itself. First, we create a matrix using signed 8-bit integers so that the determinant can be calculated accurate or nearly accurate using integer arithmetics. Then we add to each matrix elements a random value from Gaussian distribution of known derivative. And we can calculate a stochastic method to calculate the denominator. And then the denominator is calculated using StatisticalTaylorExpansion. Then we calculate result error deviation as we shown here. You can see for the matrix size from 4 to 8, for the input noise from 10 to the 17 to 10 to 1, and the error deviation is very close to 1, except at one point at 10 to the minus 7 for the input noise and the matrix size 8. The reason for that is at that point, the calculation involved significantly larger than 53, which is the significant digit count, 54, which is the significant digit count in floating point arithmetics. So it's generated rounding errors. And that's the general trend. Since we are using floating point arithmetic as an underline, when delta x goes upon 0, we will see rounding errors. And we can these calculations compare a data set with a static property calculated by StatisticalTaylorExpansion, so it's called distribution test. In contrast, there is another test. Basically, we can calculate the randomized matrix times the adjective matrix and minus the determinant of the randomized matrix times the identical matrix, right? So we instead compare data set with its statistical distribution. We compare data one by one in two data sets, and this is called a value test. In the value test, we can see the error deviation decrease linearly with the input noise as shown here, and it is for all matrix size. So these are two typical tests we will encounter in using StatisticalTaylorExpansion. And the distribution when the error deviation is close to 1 is always normal. That is due to central limit theorem. Well, the distribution for the value test is a delta function, and when the error, when we specify the input uncertainty better, the result is closer to a delta function, as we can see later. Now let's compare math library function and the StatisticalTaylorExpansion. Also, use stochastic approach. Right here, I have listed 4 most fundamental library functions: exponential, log, sine, and power. And for a pretty wide range, I'm to and a pretty wide uncertainty or precision range, And you can see all the error deviation are extremely close to 1, except at the sign, which I listed 2. One is very close to 1, another one is slightly less. I'll show you why. First, let's test the round trip um, um, error without added noise for power function, right? For using this formula, you can see in the range, the error deviation is, between 0.5 and minus 0.5. And yeah, so that basically say how much numerical error it has in power function. This without added noise. The second one is, let me show you what happened to the sign x, why there are 2 numbers. You can see this is the error diffusion for different input and the different x. We know for sign x, it is second derivative is 0 when x equal to plus and minus pi over 2, as we see here, right? That will go to 0. For the area very close to it, same thing, until the noise is big enough. If we calculate overall error deviation, it's 0.978. But if we include those 0 regions, it's 1. So that shows the typical behavior at a distributional pole. Let's discuss our third application, polynomial. First, let's continue on discussing on the distribution pole. We'd like to look at error distribution for this function, x plus minus 0.2, with a power of n equal to 2 or 3, and x equal to 0 or 0.2 or minus 2. We can see first, when n equals 3, x equals to 0, we know at this point both the first and the second derivative are 0. We see a typical delta function, and this delta function will be narrower when the input deviation is reduced from 0.2 to a smaller number. Second, we see when n equal to and x equal to 0, we see it's a left-sided delta function, as shown here, right? That is because the second derivative is positive. And we can also see this transition for n equal to 2 and from 0 for x from 0 to 0.2, right? You can see a small change. It is agreed with our previous claim that it is continuous in the parameter space. And we also can compare n equal to 3, x equal to plus 2 or minus 2. You can see they are mirror image of each other. One left-sided, one right-sided, because their second derivative are opposite to each other. So the diffusion, the second Taylor can accompany the distribution pole who has error distribution of 0 and whose error distribution is continuous in parameter space. Now let's look at the rounding errors. How a StatisticalTaylorExpansion treats the rounding error now, which can be improved. It can be proved either experimentally or theoretically that the rounding error is uniform distributed with least significant bit. Using this formula, we can change floating number x into x plus delta x, which delta x is the deviation of uniform distribution whose range is a plus minus 1. And we can see how effective this strategy is. We can see the dotted line is it is the calculate error deviation, and the solid line is is calculated by this equation. Traditionally, the solid line is called a residual error, but I have to point out it's actually rounding error here. Why? Because for the x to the power of j, when j is big enough in the floating point representation, x to the power j becomes 0. So the dashed gray lines here basically show at which stage, at which order, this x to the j becomes 0. You can see they are less than the summation of 225 here. So there is no residual error per se in this formula, or in other words, all the residual error is due to rounding error of adding xj, right? You can see is the calculated deviation follows the trend of the rounding error pretty nicely, and the overall error deviation is 2.6. The next application is faster Fourier transformation. Before talk about faster transformation, we need to have some discussion on the foundation for faster Fourier transformation, discrete Fourier transformation. So we have a wave which is small x with index k. We can transfer to its spectrum using this function, and we can transfer the spectrum back to the wave using this equation. And I have to point out, DFT is not strictly continuous Fourier transformation. It has a big modeling error. Namely, if we transfer a sine function, depends on the frequency, we can get a delta function or a much wider function, and the phase can be pi over 2 or 0. And the reason for that is the DFT has a limited range in time domain, and it has assumption that the waveform repeats itself outside its domain. Here, in the first case, if when we if we apply this function and result in a perfect sine wave, then we got a delta function in the transform. On the other hand, if we got half the wave and we then have this kind of repeat, we have pretty wide peak. This can be proved mathematically, and this is a phenomena in any of the mathematical library. Another problem is the library sine function has a lot of the numerical error. Let's first define an ideal library function called quartz index function. In FFT, the index is limited to pi over 2 to the n power times j. So instead of using a floating point x, we can use j as our input. And first, we construct sine x between 0 and pi over 2 from sine x between 0 and pi over 4, and the cosine between pi over 4. Then we extend sine x to all j using symmetry and periodicity of the sine function. Once we have that, we can compare our quartz sine function with library sine function. You can see that's how we constructed between 0 and pi over 2, a quarter pi. The sine is perfect. But beyond that, we start to see error. And this kind of error increase almost linearly with the x. And if we compute cosine x divided by sine x, we see this kind of spike in addition to this kind of error. And this kind of spike is 2 order of magnitude larger. In fact, if we use cotangent sine x, the error is even larger. Now let's look at FFT of quartz sines for sine cosine signals. First, we can see that error deviation is 1 regardless of FFT order from 2 to 16. The only difference is when the FFT order is less than 8, the sample size is less than 2 to the 8, which is not enough. So you can see some numerical instability here for statistical characterization. But other than that, it's a pretty close to 1. And when we do a forward followed by backwards transformation, we see the same pattern, that namely the error deviation decreases linearly with the input noise deviation, regardless of FFT order. This is quite similar to the what we see to the distribution test versus the value test. And because these pictures are identical for all frequencies for both sines and cosines, we can pull all the data together as a sine and a cosine signal. And then we have to look at a little bit more detail. Suppose we do not add any noise, and for the spectrum itself, for the sine and cosine, they are mostly 0 except at 2 peak. So for the forward, we have to use mutual cancellation to get rid of data in all places except at 2 peaks. So the mutual guarantee that the uncertainty increased faster. In the reverse transformation, we have to spread peaks to a whole waveform so that the change of uncertainty is a slower increase. So even the 2 formula for forward backward reverse transformation looks similar, but because of data differences, we can see some differences. And here, without the noise, using quartz signal, we basically plot the error deviation and uncertainty mean for different order. You can see for the forward transformation, the uncertainty increase exponentially with FFT order, but for the reverse transformation, it's much slower. And you can also see, you can also see that for the forward, the error deviation reaches equilibrium pretty fast when the FFT order is larger than 6. On the other hand, it takes a while for the error deviation for the reverse to reach equilibrium when the FFT order is more than 12. And also the stable error deviation for the forward is less than, it's about 0.6, while the stable one for the reverse transformation is about 0.9. Both are pretty decent. And when we look at the FFT, we look at the error distribution, we find the forward is more like a Gaussian distribution, a normal distribution, but with a peak at 0. Well, we see some structure on top of the Gaussian distribution for the reverse transformation, showing that the reverse transformation is more sensitive to the numerical errors in the quartz sine function. Now, we can repeat the same procedure using library sines for sine and cosine. We know library sine has a much more noise. We can see that for the forward, it's still close to normal distribution, and but for the reverse, we see a much more structured the error distribution, right? And this consistent with more sensitive of the reverse transformation to the numerical errors in the library function. And in fact, if we look at the reverse FFT spectrum, we see that for the real and image, for the real part, as well of the FFT spectrum, we see structured spectrum with a resonant like, and this peak increase with the time index. This is not surprising because we know the error in the numerical error in the library function periodically and increase with x, right? And so this is a manifest of that. I call it the resonance of numerical error. And this resonance can easily and mistakenly taken as real signals. And one manifesto of this numerical error is you can look at the error deviation increase with the input signal frequency. This is also expected, right? And but when we do a round trip, meaning a forward and reverse transformation, we no longer see this kind of resonance. In fact, when we calculate, when we carry out this, not using StatisticalTaylorExpansion, but using some library function, we found a very consistent result. So now we can look at the error deviation using library signs for sine and cosine, and we can compare this is a forward. We can see still has a large error of 1 as the error deviation, but when the input noise goes to 0, it has slightly error deviation is about 1.1. But when we compare to the reverse, we can see the reverse input noise increase with the FFT order when the input noise is approach 0. This is 17, 10 to the minus 17, 10 to the minus 16, 10 to the 15. So in this also shows that the ideal coverage region in the reverse is smaller than the forward. Both are consistent with the error distribution. Now, let's use another signal, a linear signal. A linear signal increase with the index, right? It's a transformation. Is this function which contains cosine divided by sine? As we know, the cosine divided by sine is much noisier. It has a larger numerical error at the peak than the sine. So we would impact the using linear is more noise. But before we started to use cosine, the clean one, to see what's the behavior. We see still a large error of error deviation very close to 1, and with some area, this is an ideal coverage with some proper coverage area very close to 1. And when we look at reverse transformation, we again see smaller ideal coverage region, and also the proper coverage region. And what if we use what if we use the library sign for the linear signal? Here is the spectrum for the
use a quad signal, right? If we use a library sign, we find that for the quad can still bind the error. Well, when we use a library, the error is not binded, right? It's a fly everywhere. And if we look at the error division map, we find the error the the ideal coverage region is much smaller using library sign, and even smaller using reverse for the reverse transform. And also for the reverse transform, the error deviation can no longer achieve purple coverage region, right? If we can imagine to extend, and also, the area becomes smaller when after the order increase. We can extend this line here, and we can find at after order about 24, we cannot no longer achieve ideal coverage region and or purple coverage region. So in another word, FT breaks down when the FT order is more than 24. And such breakdown is not easily detectable using conventional floating point arithmetics. Now let's look at the round trip. Even we know that both when efficiency input noise is very low and efficiency order very high, we cannot achieve ideal coverage or proper coverage. But in the round trip, we see a plateau area which has um, error deviation less than 1. So this is due to dependent tracing. It is essentially the problem in the forward and backward has been canceled out. And yeah, this is basically C show without error. When we increase the effort order, both forward and backward the uncertainty cannot track the value error efficiently. You see for the forward, the error at order 18, the error deviation is 10 to 2, and for the reverse is 10 to the 4, right? So basically, this tell that StatisticalTaylorExpansion breakdown when you cannot properly specify the input uncertainty. In this case, the library contains too much in the macro error. And we can add noise, Gaussian noise or white noise to the input until we have a proper ideal simplification of the input noise deviation. And here is for different for the to the 18 order samples for different signals for different library function. How many input coverage? How many input noise we need to add to achieve ideal coverage? And this is a way for us to make sure we have a correct implementation of StatisticalTaylorExpansion because there are ideal coverage exists. It's also defined the ideal coverage region. For example, for the forward transformation, for the side, we can see anything about 10 to 16 should be good. On the other hand, for the linear signal using library function, we can see 10 to the input noise has to be more than 10 to the minus 3. And here is our error spectrum for the linear signal using library sign function. As we know, for the reverse, the error doesn't seem to be bounded. When we add noise, we can see noise of 10 to the minus 3. We can see both forward and reverse transformation become Gaussian like, regardless of what kind of noise you add, whether white noise or Gaussian noise. And the round trip become a perfect delta, regardless what kind of noise you add. And here is the previous chart for the error deviation and uncertainty, how it grows with the FTC order. If I add 10 to the minus 3 noise, we can see both the forward and the reverse error deviation become perfect one, and the round trip error deviation is much less than 1, although it increased with FTC order as we expected. And we can also look at the uncertainty, right? For forward, it grows exponentially with FTC order. That is understandable because for each addition of FTC order, you basically add one more step of addition of two multiples, right? So the amount of calculation goes exponentially with the FTC. The variance goes linearly with FTC order, actually as a square root 2 here. Square root of the FTC order. Because variance goes linearly, so the uncertainty goes square root of the FTC order. And because for the reverse transformation, there is a division of 1 over 2 to the L, right? So the reverse train is 1 over square root of 2 to the order of transformation. And you can see in both cases, the input precision of 10 to the minus 3 or input uncertainty of 10 to the minus 3 is covered ideally. The final application, I will use regression to show that StatisticalTaylorExpansion can trace catastrophic cancellation. Here is the regression. We know sine 0 and cosine pi over 2 equals 0, sine pi over 2 and cosine 0 equals to 1. And we can use this formula to regress for other angles between 0 and pi over 2. And also this formula to regress for other angles above pi over 4, right? But there is a problem, as we can see. This formula is actually and because cosine alpha is cosine beta minus sine alpha times sine beta, when both alpha and beta are pretty small, this is 1. So this sine alpha plus beta divided by 2 embeds a catastrophic cancellation when the angle goes to 0. And here is what we can see. You know, when the angle, the index of this go to 0, we can see when we regress the j pi over a to 18, when the index go to 0, we can see the precision actually increased pretty fast until 10 to the minus 7, starting from the half pi over 2, right? So this you can use in contrast. If we use cut size, we see that precision is a constant all over. So using this this chart, you can see when the catastrophic cancellation happens and happened by how much. Finally, I will go to a summary and the discussion. I'll give a summary and then go over improvement needed. And finally, I will present some possible connections to quantum physics. The summary. First, we achieve to calculate the result, mean and standard deviation for any analytical function if we know the input, mean, and standard deviation, and we can calculate reliability of the result if we know the input uncertainty distribution type and the sample count. And we can use precision to measure the quantity when the value is not zero. The mean is not zero. And also we can use ideal coverage to validate any application of StatisticalTaylorExpansion. The ideal coverage has to exist, means the application is correct. We also find the need to recount the library math functions to output an uncertainty with each value and to minimize the numerical errors in it. And also because requirement dependent tracing, we have not so much flexibility as in the traditional numerical algorithm, and we need to re-examine our traditional numerical algorithms to be consistent with StatisticalTaylorExpansion. Finally, of course, we need more validation for StatisticalTaylorExpansion. Although StatisticalTaylorExpansion has shown a great potential, they still need some improvements. First, we need to expand the bounded momentum, zeta, and kappa to all distributions, as well as to discrete distributions. Second, we need to do some source tracing. For example, for x plus y, the first formula gives the result ideal leakage from the input leakage, and essentially shows it is a weighted, it is a deviation weighted average of input leakage. And this could give us an idea if we want to improve the ideal leakage of the result, which input we should collect with small samples. And also the second formula shows the result ideal leakage from the of x times y from the input leakage. It's essentially the same weighted average. And also we need to improve performance by parallel processing and hardware, because StatisticalTaylorExpansion contains a lot of sum with the exact same structure, which is ideal for SIMD, single instruction multiple data. Another thing is we need to improve to achieve ideal coverage for random errors in hardware. Right now, the StatisticalTaylorExpansion assume actually account for all the random error as part of input, which is not enough, because in real time there's a lot of random error could generate as well. In hardware, we can reflect the change in the result uncertainty. This can also be done in software, but it's going to be extremely slow. But in hardware, it should be easy and straightforward. Another problem is, in StatisticalTaylorExpansion, the value and the deviation can be compared. But in the calculation, the variance is used. So this this actually limits the range of the uncertainty to square root of the range of the value. It is, if it's possible, we can repurpose the sign bit in a floating point representation as a part of the exponential bit. So to generate unsigned floating point to hold variance. In this way, we can have a comparable range of values and the uncertainty. And another thing here is from the formula for matrix inversion, we know the expression for StatisticalTaylorExpansion could be very complicated. And this actually calls for using analytical software like SciPy or Mathematica. Finally, there's some interesting thing about StatisticalTaylorExpansion. It has possible connection to quantum physics. We know when kappa goes to infinity, the result variance for function when it's used precision as input diverges, and does that remain us as quantum normalization, right? Basically, if you cannot count the result for a perfect distribution, but you can calculate when the sample count is limited. In a reverse token, is when kappa is equal to when kappa goes to 0 due to measurement, any variance of function with precision input converges. So that could be used to explain quantum waveform collapse, because when the variance diverge, that means it can exist anywhere in the space. But when it's become limited, that means it can exist in that local area or at that point. Another thing here is we have not discussed too much about uncertainty bias, namely the mean is different from the value without uncertainty, right? And that could have a lot of effect. For example, can it be used to explain lamp shift? Yeah, though there is a lot other things we can discuss, and but we need to put StatisticalTaylorExpansion in a solid ground first.